Hello everyone. So today we are going to discuss a topic that is vulnerabilities and their mitigation is in DNS. DNS stands for domain name system. Basically, DNS is used for resolution of any given IP, that is any given address, that is you have www.google.com to the corresponding IP address. Means for accessing any web resource by using your browser, you need to first access the particular device, that is a particular IP. So for converting this name, that is google.com, into a particular IP, we need domain name system, which we will discuss further. So in this presentation, first we will have a brief introduction about what is DNS. Then we will seek the objectives about what objectives do the DNS system provides to the regular customer that uses the internet and how it affects basically. Then we will see what is DNS security and which gaps are being addressed by the research that is going on today. Then we will see the literature review, that is how the research is going on and on what topics actually we are trying to increase the awareness among the corporate sector so that they can mitigate the risks. Then we will talk about the methodology that the researchers are trying to propose in order to mitigate the risks. Then finally we will conclude the discussion with a perspective of what are the possibilities or of research in this domain and how we can further increase the security of DNS resolution by implementing some basic policies. So as we know in the introduction part, each internet connected device has a unique IP address, and since each IP address is unique, so we can use it to find any machine, right? So we can use it to find any of the machines that is connected to the internet. DNS translation translates domain names to IP addresses, allowing browsers to load internet resources. As I mentioned earlier, in order to get a resource or in order to access a resource, we first need to convert the domain name, that is www.microsoft.com, to a particular IP address so that we can load the resource into our browser. Okay, so as we can see in the example given here, example translating www.onlinesbi.sbi into a computer friendly IP address like this. So we cannot directly access using the domain name, right? Means for a machine to understand that which particular web server we are trying to communicate, it has to be a unique publicly exposed IP address. Publicly exposed means any resource which is connected to the internet has to have some ports and a public IP that is accessible from the internet, right? Which is not inside the organization's internet. So we will talk more about this later in the slides. So let's go below. Okay, so objectives. So first objective is address the event that the unauthorized third party gets sensitive or unauthorized information using DNS resolution. So what we are trying to say is when a particular person tries to get information about the IP address, he may be a bad actor in the scene and he might get unauthorized information about the company or about the server which he should not be getting, right? So suppose you should not be able to fetch some private SSH keys, for example, so during the DNS resolution. So if the user is able to access any of such information, then we will say that it is unauthorized third party access and we need to avoid that, right? So the second point is understanding that data involved in DNS resolution is of great value and high privacy. As I mentioned earlier, examples like SSH keys and the encrypted passwords that are being stored on the web server are of great value, and they should not be basically exposed to any mm, bad actor or person trying to fetch these data using DNS resolution. Third, we will see how to avoid being blocked by DNS server to perform a whole IPv4 network scale measurement within an acceptable length of time. So if we are trying to basically establish a particular metric, that how many DNS resolvers at present are basically vulnerable, then we need to perform a whole IPv4 network scale measurement, right? So, and for this kind of measurement, one needs to pass at least 40 to 50 or even more requests to a particular DNS resolver to understand if it is causing information leakage, or it is vulnerable to the external internet, right? So what I'm trying to say here is, if we are trying to make so many requests to a particular DNS resolver, then it might be the case that due to security policy it might block us. But our algorithm should be such that it should be um, resistant to such mm, policies, and using very small amount of requests we should be able to identify whether a given DNS resolver is malicious, is basically vulnerable to attack or not. Okay, so let's go to the next slide. So the first gap that is we are addressing is, due to immense internet traffic increasing each day, research to improve DNS security have been proposed. As I mentioned earlier, although there has been research in this domain for for many years right now, but still companies and corporate agencies don't pay much attention, especially the smaller agencies that don't have the capital to do so. So what they do is just ignore these facts and basically continue with the traditional DNS resolution parameters, and as usual the data breaches and other things occur. So we are trying to assess the security status of open resolvers for entire IPv4 addresses on the network, concluding that a total of 1.8 million open resolvers handle DNS requests. So if I try to elaborate on this point, what are open resolvers? So open resolvers are those basically DNS resolvers that do not have a particular authentication associated to them, right? So if a DNS resolver is not authenticating which particular from where the request is originating, then we say that open resolver is handling our request. So this has the problem, and open resolvers are significant in this domain because the amount of traffic they are handling. As mentioned here, over 1.8 million open resolvers handle DNS requests, and you can assume that each DNS resolver handles about millions of them. So if these many number of open resolvers are there, so basically we need to fix those issues. So the next point, reverse DNS lookups of reserved addresses based on DNS queries are being used to quantify information leakage. Basically what we are trying to do is, when we are trying to fetch a DNS resource, as I mentioned earlier, we use a domain name, and then we basically transfer it to the DNS resolver, and DNS resolver gives us the IP address. But if we can also do the opposite thing, that is, we transfer it the basically we query with the IP address and it gives us the domain name, right? So that is called reverse DNS lookup. And suppose we are somehow we manage to get the internal IP address of the resource, then that address would be called as reserved address. So those reserved addresses and their reverse DNS lookup can be used to quantify whether the DNS resolver is a leaky resolver or not. Next is implementation of information leakage preventive policy and perform simulations to evaluate the policy. basically there will be some policies that we need to put in place in order to assure the government officials and other governing bodies that we are not in stand of any information leakage from our side. Okay, so next point, literature review. So as I was mentioning that currently there have been many researchers working on this, so we will be talking about two of them for just educational purposes. So first one is security analysis of DNS open resolvers by continuous and ambulatory detection. So this is a 2021 research paper, and you might ask it in the comments if you want the research paper, or you need the link to the particular site, so I'll provide it there. So they conducted a many quantitative and comparative analysis, and which finally reported an illegal operation of open resolvers is a crucial problem to solve. So this is just a simple way to explain that they conclude, since we are trying to basically find out whether open resolvers are causing any problem or not, so we must quantify it with respect to other resolvers that are in market and check whether any vulnerability exists or not. So they have done that and conducted many quantitative and comparative analysis of that, which we will see next. Okay, so next is measuring information leakage of a DNS server. So information leakage, which we will discuss later in the video, is basically a problem in DNS servers that basically allows the agent or the bad actor to steal information that he should not be able to steal actually. So what these guys have done is they have utilized a popular utilized rank first query in place of regular sequential query. As I was explaining for previously, when we query the DNS, right, so we are basically querying with a sequence of requests to it, and as a result it replies or sends the response in that sequence only. So this causes a lot of repeated requests, I will say. So in order to avoid that, so that we are not blocked from the DNS server, we will use a specified query number, that is a few of the queries we will filter out as to which are allowing us to filter whether the DNS resolver is leaky or not. So we will only use that, and how we will basically arrange that, we will arrange that using a popular rank of the query, and then we will basically ask for the DNS resolver to fix that. Okay, so next is basically the methodology of the first part, that is the open resolver and their vulnerabilities. So for those of you who do not know what is a DNS lookup, so I will take a note on that. So when a DNS client sends a request, the first responding server does not provide the needed IP address. Instead, it directs the request to another server that is lower in the DNS hierarchy, and the one to another until the IP address is fully reached. Basically, suppose we take this example to another page. Okay, so in this, suppose I try to explain that this is the, I think the image is not visible. Okay, so suppose this is the DNS client, we are the browser in it. Okay, so we need the fixrunner.com, and we will ask it to the DNS resolver. So what will happen is, so this DNS resolver will send this to the root server. Okay, so root server is basically the first server that DNS resolver will contact with this domain fixrunner.com. Root server will send it that it is .com has been a particular IP address, that is .com of the fixrunner.com has to be handled by a particular server, and the address of that server will be sent by the root server. Okay, so once it has this, it will send to the .com TLD server. Now what is this TLD? TLD stands for top level domain. So top level domain like .org, .in, .com, all these are top level domains, under which there will be like Microsoft.com, Google.com. So these are basically the below top level domain basically websites, right? So what will happen is it will basically search in its database whether there is fixed runner or not. So once it finds fixed runner, it will say that okay, I have found it, and suppose it is in x.x.y IP address, so it will send that, and we will ask the authoritative name server for fixedrunner.com. So suppose there is an authority that is basically keeping logs of all the IP addresses associated with fixedrunner.com, google.com. So that will tell us that okay, we have fixedrunner.com and we have a particular IP associated to that, and that we will return to the DNS resolver. And once that is done, what we will do is we will finally ask for the particular service which we are trying to access, like login.fixedrunner.com or any particular. So we are trying to access the main page. So the main page will be basically sent to the DNS cache, as you can see, and then DNS resolver will send it back to the DNS client. So this is how a particular domain name is basically translated into an IP address. So now we will go back to our slide. Okay, so I hope this is clear. Now next is the security analysis of DNS open resolvers. So what we can do to basically analyze the security scenario of open resolvers is we can simulate a scenario, and we can probe the open resolver, and we can basically filter out the responses that are being wrongly accepted or wrongly processed by the open resolver, and then we can basically classify whether it is a faulty or not. So first is we initiate the DNS request to various destinations, aiming to identify open resolvers among contacted IP addresses, right? This part of the local server, that is we are trying to reach the internet and find whether we are contacting an open server or not, open resolver or not. So once we do that, the next thing is open resolver step 2, step 3. So in step 2, what we are trying to do is we are trying to contact the web server of a particular service, suppose mysql.com. So mysql.com will return the payload, that is the data which we are trying to access. So then we will accept it in the accept module, that is 4. So it receives the response packets from the open resolver tasked with the processing these packets, right? So what we will do next is filter the response packets and discarding the invalid ones based on predefined criteria, and forwards the valid packets to the process module. So this is how we will use a local server to analyze the open resolver using a web server that we are trying to reach. So I hope this makes sense. Basically this we are trying to just get the data, and the further processing will be done basically in the later stages of the architecture. Okay, so yeah, so then what we will do is we will have to identify the packet and see whether it is a valid packet or invalid. So if the packet is less than 20 bytes, it will be filtered, because the header size, as you can see, is basically 12 bytes, right? So if it is 12 bytes header and basically 8 bits further for flags and all, so if it is less than that, we will clearly say that the header is missing. So if, and next, if it has incorrect ID or QR fields, result in filtering incorrectly as the DNS proper format is there. Then the opcode field, if it doesn't match with the requested domain, then the packet is filtered. Packets with a different name flag from the requested domain. Suppose we wanted google.com, but it came online SBI. So those are filtered basically. So name field typically contains the domain name that was queried. It typically contains that, but if it doesn't, then we filter that. Okay, so yeah. So for the open resolver part, we see that there are approximately 1.8 open resolvers that are identified. Secondly, significant number of servers detected being incorrectly used, indicating misconfigurations, right? So there, that is the point where malicious activities can occur, and we need to basically mitigate them, right? The study also noted the existence of ghost resolvers. Ghost resolvers cache domain names that have been eliminated, potentially providing outdated or inaccurate information in the DNS resolver. Suppose you had a website on a particular domain, right? And suddenly you asked the domain service provider to delete your website. So what he did, he basically stopped your service. That is, you can no longer basically access it via the domain. But suppose someone had your IP address, right? Suppose someone had stored your IP address. So what he will do is he will directly try to fetch your IP address, and he might be able to do that. And why he will be able to do that? Because the log in the DNS resolver has already been made for that particular allocation, and it has not been removed. Only the domain name has been removed, but the IP address associated to that service has not been removed. So this is how ghost resolvers cache domain names, and that we need to resolve. Okay. So the next thing is information leakage basically. So in information leakage, we have three types of information leakages. The first is DNS information leakage, is divided into three categories. First one is client side leakage. Second is the transmission, basically the transmission process, and if leakage occurs in that. And the third is server side leakage. So we will, in this particular video, we will discuss about server side leakage. So information of the what on the server side, we need to consider three major topics that might be vulnerable to this problem. So that those are information of the DNS server, DNS resolution caches, and DNS resolution history. So all these are important data points that the malicious actor should not be able to guess or basically gather using DNS resolution. So these we need to protect. So next, yeah. So the first problem in this particular domain is storage division. I think this is shorter in size, so right. So what we are trying to do here is we are trying to understand a particular problem of storage division. So in this we can see an extranet client is trying to access two IP addresses, that is 1.a.b.99. INADDR stands for internal address, and ARPA stands for address routing perimeter area. So this is basically, ARPA is basically a top level domain service zone, basically top level domain zone that is associated with reverse DNS lookups, as I mentioned before. And INADDR stands for the format that we are using here, that is reverse the DNS and then look up it. So before understanding that, we must come here and see that mail.com has the public IP as 10.0.0.1, and the private IP that should be basically within this zone and should not be exposed outside is 99.b.a.1. Similarly, help.com and dns.com. So what should be the case is, the extranet client, when he queries with this particular query, should be able to get, that is mail.com. Why? Because it is the reverse of that. 10.0.1 is the reverse of 1.0.0.10, that is 10. So the extranet client should be able to access mail.com by reverse querying this, but the external client should not be able to access mail.com using this particular IP address, that is 1.a.b.99, because this is the internal IP address, right? So why is this occurring? Because this extranet resolution server has all the files or all the basically DNS records in the same file, that is in the same place. So since it is the same place, it is quite natural that it might be able to get that 1.a.b.99, and then it will basically transfer it to mail.com. But if suppose these both are in different files, then there would have been no problem. So this storage division we have to make. So next is network host. Network host is, suppose we are having this extranet resolution server and intranet resolution server. So what is intranet resolution server? Is for this intranet client that will access it and then get the service. So this intranet client will say that, look, get me 99.b.a.1. So then this intranet resolution server will point to mail.com, and this extranet client will say, look, get me 1.0.0.10, and then it will fetch it mail.com. Cool. So what the problem here is, the extranet client should not be able to query this particular intranet resolution server, right, with the query like 1.a.b.99, right? So this should not be able to query this particular intranet resolution server, or better I would say that intranet resolution server should not accept any queries from extranet client. So if we block this particular line, right, this particular line is blocked, then we are able to basically prevent extranet client from getting internal IP. So the methodology used here is basically we will conduct an entire IPv4 scale analysis of how many DNS resolvers are there that are basically vulnerable to these two problems, and then we will get, like, as these guys have got almost these many hosts with 53 open ports, resulting in these many DNS servers being successfully detected, right? And how they have done this? So okay, so by using this algorithm, they are basically able to get how many DNS resolvers are basically vulnerable. So you may go through this algorithm. This is basically the implementation of how we can detect the faulty packets from the DNS resolver. So this is the basically algorithm associated to that, and this is the all the explanation for that. So what we are basically trying to do is, first we are trying to get the servers list, right, the IP addresses that are associated to the services in a particular DNS resolver. We are trying to get that. Next we are trying to get the reserved addresses. Okay, third, what we are trying to do is we are trying to make a PTR pointer that basically points the reverse of IP to domain name, and once we are able to do that, we will just run it on the n square times on the entire set, because for each internal IP there has to be an external IP. So that is why we are using n cross n, and then we will see whether a particular query is ranked on top or not based on the mail, whether it is able to wrongly get mail.com with the private IP or not. So that is how we will calculate the top rank query, and we will use it to basically lessen the query numbers. So this is the basically implementation of that. And after that, what we have to do in order to basically prevent these two vulnerabilities is set the two DNS servers to separately resolve the internal domain and resolve the public domain name, right? So both of them should be stored separately, and the resolution, that is separately store and strictly isolate public and internal DNS resource records. So we need to store them separately. And in the first point, we need to provide basically two resolvers, that is extranet resolution server and an intranet resolution server, that will handle the requests accordingly. This will handle the intranet client and this will handle the extranet client. Okay, so as a conclusion to my talk, we have indicated that the causes of based DNS server queries and information leakages, and proposed a corresponding measurement approach. And DNS queries can basically further be dug into using cellular IP addresses that are basically used on the mobile phone across the world. And basically we can use it to characterize the information leakage, how and which levels of information leakage are basically probable in these days. And basically this will ultimately reduce the adverse effect of data breaches and stuff like that. And secondly, we can explore the methods of all possible intranet addresses of zone that are successfully being resolved, despite the fact that it should not have been in that case, right? So we need to explore the methods, how can we stop that. So yeah, that's been it, and I hope I was able to deliver the content. And for any queries or discussion you might have, please use the comment section of this video. Thank you.